Hello, my name is Aniket Bose, and in today's lab we are going to understand the IV characteristic of different kinds of diodes. So what is IV characteristic? The concept is simple. If we apply a particular value of potential difference across any kind of electrical or electronic device, then a particular amount of current will run through it. If we change the applied potential difference across the diode, then the current running through it will also change. We can take pen and paper and write down this potential difference applied and the current running through the device, and we can generate a table in this way. So we can generate these kind of tables for different devices, and if we observe carefully, these tables will be unique for each of the devices. That is, those tables will be like fingerprints of those devices. That's why this is also sometimes called device characteristics, and because in our case the tables are relating currents and voltages, so they are called IV characteristics. Now in our case we are not going to do this manually. That is, we are not going to apply the potential difference across our diodes, then measure the current running through the diode and write it down. We are not going to do it. Instead we are going to use a software and a device which will do it for us. So the software is going to generate different amounts of voltages across our diode, and then it is going to measure the current corresponding to those voltages, and it will plot the potential differences applied in the x-axis, and then it will plot the current running through the devices in the y-axis. In effect, it will generate a graphical view or graphical representation of the IV characteristics automatically. Now there are two problems related to the current. Because the device we are using is this ADLM 1000, it has a ADC inside it, so there is a resolution corresponding to that ADC. The minimum value of current that it can measure without any noise is 5 milliamperes, and there is also a protection circuit inside it which can measure a maximum value of 200 milliamperes. So for example, if we had this circuit where we are generating a 5 volt DC on channel A, and we are connecting a 10 ohm resistance across the channel A and a ground, then according to Ohm's law, the current running through the circuit should have been 500 milliamperes. Now because of the protection circuit, the ADLM kit will not be able to generate this 500 milliamperes. So what it is going to do, it is going to drop the 5 volt DC to such a voltage value such that the current running through the circuit becomes 200 milliamperes. So there is a range to the current which we can properly plot on the graph, and corresponding to these current range we need some load resistance values to properly plot the graph. So that's why I am using this 100 ohms. In our lab manual, we were given to use a 1 kilo ohm resistor in the circuit, but I am using this 100 ohms particularly because of this reason, that so that I can generate the IV characteristic properly. So here you can see I have connected a trim pot, and I have already set up the resistance between the third pin and the second pin to be 100 ohms, and the anode of the diode is connected to the second pin, and the cathode of the diode, which is the silver marked terminal, is connected to the ground of the ADLM kit. The channel A here, the yellow wire, is going to generate a very low frequency triangular voltage waveform, and it is also going to measure the current running through the circuit, and the channel B is going to measure the potential difference across the diode. So now let's build the circuit. Here first let's check the resistance across the second and third pin of the trim pot. So you can see it is around 100 ohms. Let's build the circuit. Here you can see this diode, the black terminal is the anode terminal, and this silver strip that you can see, this terminal is the cathode terminal. So we are going to connect the anode terminal, which is completely in black, to the second pin of the trim pot. So let's do that. Now the channel A goes to the third pin or the last pin, and channel B is in the second pin, and the ground is connected to the cathode of the diode. Also need to connect the ADLM, so I have connected it. Now let's come to the software. So here you can see I am generating a 10 Hz triangular voltage waveform on the channel A, which varies from 0 volts to 5 volts, and the channel B is in high Z mode, that is, it is only going to measure a voltage. To plot the IV characteristic, I am going to use this XY plot. Here I can set the x-axis to channel B voltage and y-axis to channel A current. So that means we will run the circuit. The y-axis will show the current running through the diode, and the x-axis will show the voltages generated across the diode. Now let's run the circuit. So here you can see the green colored trace is of the channel A voltage, the orange colored trace is of the channel B voltage, and the channel B voltage corresponds to the voltage across the diode, and the cyan colored trace is of the channel A current, which corresponds to the current running through the whole circuit, or that same current is the current running through the diode. So now let's come to the IV characteristic. You can see the IV characteristic is generated like this because we have not set the scale properly. So we need to set the scale properly. So let me stop the circuit first, then we can set the scales here. Now if we run the circuit again, you can see this beautiful IV characteristic of the diode is generated. Now we can stop the circuit, and then if I turn this persistence mode on, then I can reverse the polarity of the diode on the breadboard, and then I will be able to run the software, and it is not going to affect the previously generated IV characteristics. We will be able to see multiple number of IV characteristics on the same graph or on the same. So if I run the circuit again, you can see the IV characteristic of the reverse polarized diode is showing here. So there is no reverse saturation current for any voltage from 0 volts to 5 volts for this simple diode. Now let me change the diode again. So I am going to use an LED now. Now you can see the IV characteristic of the LED is showing here. Now let's change the LED to a simple Zener diode. Now I am going to run the circuit. So here you can see the IV characteristic of the Zener diode is also showing here. So the first one is of the normal diode, and the second IV characteristic is of the Zener diode. Now we can check the knee potentials from here. So the knee potential for the normal one is 0.59 or 0.6 volts, and the knee potential of the Zener diode is 0.7 volts, and the knee potential for the LED is around 1.8 volts. Now we can reverse polarize the Zener diode and we can check the IV characteristic, where we can see there is some reverse current being generated. So let me put the Zener diode in reverse polarity. So I have put the Zener diode in reverse polarity. Now we can run the circuit. So you can see there is some reverse current that is coming, reverse saturation current here for the Zener diode, and it's starting from around 2.8 volts. So the part 1 where we need to study the IV characteristic for the normal diode, and there is also this part 4 where we need to repeat the part 1 with the Zener diode. So we have completed both of them, and I have also included the LED here. Yeah, we can move on to part 2. In part 2, we are going to study the input and output voltage waveform of a half-wave rectifier. What half-wave rectifier do is that they take input voltage waveforms of sinusoid nature and transform that in the output to DC. Now to do that, we have taken this diode and resistance in series, and the resistance, as you can see, is 10 kilo ohms. And to generate input voltage waveform of sinusoid nature, we are going to use this ADLM kit. In the documentation of ADLM 1000, you can see they mention that this ADLM 1000 can only generate and measure unipolar or single-ended signals in the range 0 to 5 volts. But they have also given the workaround to generate minus 2.5 to 2.5 volts. There are two pins, 2.5 volt and ground pin. So we need to use the 2.5 volt pin, which is provided on the ADLM kit, to be the reference of our circuit and not the ground. I'm going to use that as the reference, and channel B, which is the blue wire, is going to measure the voltage waveform across the resistor. That's why I'm putting the channel B and the reference to be across resistor. And this yellow wire of the channel A is going to generate a input voltage waveform of sinusoid nature. Now let's come to the software. Here we need to set the channel to generate a sinusoid voltage waveform. It will vary from 0 to 5 volts inside the ADLM curve, and we can set the offsets of the reference of channel A inside these boxes. So this is for channel A reference and this is for channel B reference. Also the vertical midpoint of all the waveforms should be 0 volts. Channel B should be in high Z mode because we are not going to generate anything. We just need to measure the voltage across the resistor. Then we are using a 100 Hz sinusoid, so I am going to set the time base to be 5 milliseconds per division. We need to enable the channel A and channel B trace. If we run the circuit, you can see the voltage waveform. So these input and output voltage waveforms are when we have not rectified properly. But to rectify it properly, we need to put a capacitance across the resistor. So this is a 100 nanofarad capacitor. I have put this capacitor in parallel to the resistor. Now we'll take a look at the output voltage waveform. You can see this rectified poorly, but we can change that. We can make it more proper by using a higher resistance value. So I have taken 10 kilo ohm and 15 kilo ohm in series, and I am going to put a capacitor, the same capacitor I have, in parallel to them. Now if we look at the input and output voltage waveform, you can see it rectified more. We can rectify it more if we put more resistance, or instead if I use a capacitor which is 1 microfarad instead of 100 nanofarads, then it will rectify more. Now let's see. So here you can see it rectified more. So why this is happening is because the capacitor stores potential across it in the positive half cycle, and when the negative half cycle comes, it discharges across the resistor. Now more the resistance value, it will discharge less, because the more the resistance, the lesser the current. So the capacitor in the negative half cycle discharges less. But if we take lesser resistance, then the capacitor will discharge more, and it will not be able to maintain the potential in the negative half cycle because it discharges fast. But if we use a lesser resistance, we can use a better capacitance to store more charge, and then for lesser resistance also it will properly rectify. Now we are going to do some calculations. For that, inside here we need to measure channel A average voltage and the RMS voltage. So we are going to measure the average and RMS voltage of the input and output waveforms. We are going to run the circuit, and here you can see the average and RMS potentials of input and output. So this is channel A and this is channel B, and here are the RMS and average values. Now we are going to calculate the ripple factor and the efficiency of rectifier. The rectification efficiency is the ratio of DC power dissipated across the load to the AC power provided from the input. Now for our case, the average output voltage, which is the channel B average voltage, is 1.61, and the RMS input voltage, which is the channel A RMS voltage, is 1.73. The rectification efficiency came out to be 83%, and ripple factor is the ratio of RMS potential of only the AC component to average potential of the output. Now to get the RMS potential of only the AC component, we need to subtract the RMS potential of the DC component. That's why we have done this whole thing because of that, and the ripple factor came out to be 0.44. In books, the rectification efficiency is much lesser and the ripple factor is much greater, but because we have used a greater resistance, that's why these values came out to be like this.